In this section, we're going to talk about many different applications for fission, including radio dating, chemotherapy, diagnostic therapies, uh, nuclear power, and others.
So it's worth mentioning that there are a lot of different radioisotopes with massively different timescales. Now, when we say naturally occurring, what we really mean is naturally occurring and we can find them. So there are shorter half-lives that exist in nature, but the idea that you're going to find something that only exists for 28 days in nature is pretty unlikely. Carbon-14 is one of the few isotopes we find often, in pretty low concentrations, and it only exists for a 6,000-year half-life. So, you know, we need to have some pretty big time frames to be able to find these things in nature. Now, one of the ways we find carbon-14, of course, is in your bones. So as long as you are eating carbon, you are naturally accumulating carbon, and thus a small amount of carbon-14 in your body. And so when you stop eating, essentially you die, and that carbon-14 in your bones naturally starts to decay. So if scientists can read the carbon-14 content in your bones, they can figure out how long ago you were alive. Now, generally speaking, this works best at 10 or less half-lives. So this really only goes back, at most, about 50,000 years. So that's really more like 8 half-lives. 50,000 years is approximately the best range for this stuff. So that works really well for kind of human history or, or primate history, I guess. It doesn't work great for anything longer than that. So if you want to look at the age the dinosaur exists, for example, you can look at the natural accumulation of other things in your bones. Potassium in the bones, for example, you can look at the natural content of uranium around the bones. In fact, if you want to look at something older than the age of man, you really need a large number of isotopes to verify the age. So generally, the standard for archaeologists is you need to have 6 isotopes that all match the same time period. And that's because some of these isotopes vary. For example, if a giant meteorite hits, right, that can change the isotope content of one isotope and make it unusually large for a period. And so getting 6 isotopes to match historically is a really, really high threshold, but it basically proves that it can be reliable, give or take 1,000,000 years. Medical isotopes, on the other hand, we want these things to get into your body, do their damage, get out as quickly as possible. The longer we have radiation in your system, the more likely you are to have secondary issues, to have secondary radiation damage. And secondary radiation damage can also lead to secondary cancers. But usually if they're applying chemotherapy, right, we're looking at some pretty serious, like dead if we don't fix this type of problems. So, we'll take the chance at a cancer later on if we can deal with the cancer we have today. So there are 2 major applications for radiation. Therapeutic radiology, and that's chemotherapy using ionization to kill cancerous tissue. But there's also diagnostic radiology. And here's where we're going to put in radiation that's not designed to do damage as much as allow that radiation to be detected. So you're probably looking at some kind of gamma radiation, something along those lines. PET is positron emission topography. So at that point, you're measuring the creation of positrons. But we're trying to do low level. We're trying to see just where these radioactive nuclides gather, right? So the middle picture is the one I'm most familiar with. That's a iodine PET. And so they're looking at where iodine gathers in the body. They can look at that shape of the thyroid and how that thyroid is gathering iodine. And what you're really looking for is an area that is very high burning of iodine that is not in the shape of the thyroid. So you're looking for like a node off the side of that organ that's burning iodine very, very brightly. And what that implies is that you have something growing much faster than it should and processing much faster than it should. And that would be the sign of some kind of cancerous growth. So one of the things that's interesting about these radioisotopes is we tend to use radioisotopes that are naturally gathered in certain parts in the body. So for example, iodine being used in the thyroid, phosphorus being used to identify and kill bone cancer. Um, so we can get that ion to go where the body naturally wants it to go, and where the body naturally accumulates it, so we can get it as close to the cancer or even inside the cancer if possible. And we're looking at, in the last 10 years, a bunch of new systems being developed, things like using natural human antibodies attached to the cancer drug, so that the antibody attacks the cancer and then the chemotherapy goes off. So you can see how they're used, and again, these are kind of interesting, although not a comprehensive list. But it's worth bringing up that all of these are reactor-built radioisotopes. So they have to be built in a way that they are exposed to radiation in order to be created. And that's a huge issue, because we have fewer and fewer nuclear power reactors running across the world, right? They're very expensive to build. We still haven't figured out what to do with the waste. And so we are already getting to a point where you have to get on a waiting list for some of these chemotherapy drugs, just because they are so hard to get a hold of. And so we really need to be building up nuclear power in the States. Even if I don't 100% agree with it, we need these nuclear powers, because we are going to need more and more of these drugs as we get older and older as a society, and for other reasons we haven't even realized yet. So how do nuclear reactors work? Well, all nuclear reactors are built on the idea of fission. We have these uranium particles, as we said, they are chock full of energy. We are going to force them to break apart. Instead of taking a million years for this thing to detonate, we want it to detonate in a big way immediately. And so we slam it with a neutron. It splits. Depending on how you slam it, it will split in different ways. Depending on what isotope you use, it'll split in different ways. But what we get out is a bunch of smaller particles, more neutrons, and a ton of energy. We'll calculate that later. So the goal here is not to have one destruction. The goal is to have many destructions. And so those new neutrons then react with more uraniums, and those detonate to give more neutrons, and we get what's called a chain reaction, where we're trying to build this up as much as possible. The ideal here is we want what's known as a critical mass. When you basically, like a line of dominoes, you keep the chain going at the same speed all the time. What you want to avoid is, most importantly, a supercritical mass, where this chain reaction occurs without being able to stop it. And that, if you get a supercritical mass and it accelerates beyond control, that's when you get an explosion. The other thing you want to avoid if you're running a nuclear power plant is a subcritical mass, where you don't have enough radiation, you don't have enough neutron radiation slamming the uranium, and the reaction slows down. And that's basically going to cause your reactor to turn off. The most expensive part of these machines is getting them started, so you never want to have the chain reaction die. That's always bad. So how do we control this? Well, the only way to block all radiation is with some super heavy metal. So lead control rods. The Chernobyl video talks about boron control rods. I'm not sure how they work compared to lead, but I guess boron is thick enough that it can block neutron radiation, right? Neutron has mass. But lead is pretty much the standard because it blocks everything. So what we have is some cooling liquid that flows through, keeping these rods cool. And then we can lower these control rods to slow down the reaction and lift them to speed up the reaction. And we talk about how this is an issue in that Chernobyl video I've put up. But this is controlled by a control rod drive, to avoid things like Chernobyl, to avoid things like the 3 Mile Island incident. This system is now on automatic shutdown if radiation is detected outside of acceptable meters. So a couple of quick things. Usually it's a magnetic system now. So if the power running to that magnetic system is hit by radiation, it automatically turns the power off to the control rod drive. Without that power, there's no more magnet. The control rods drop into place, the reactor turns off, and it gets very, very expensive to turn back on again. So, they have a lot of fail-safes in place to try and prevent that from happening, but at the end of the day, the control rods are the ultimate fail-safe. Now, the power to this control rod drive is actually no longer controlled by this power plant. In fact, in the Chernobyl video, it's not in that one either, right? They don't want this thing to get out of control, and then you can't operate the control rod drive. So it's almost always run by a secondary coal or fuel or hydroelectric power source. And usually they prefer to do something like coal because you want to be able to have power all the time, right? So you can control this control rod drive. So, when we say nuclear power is carbon neutral, right, it actually isn't, because you do need that other power source unless that power source is hydroelectric. So, again, that's not the biggest problem with nuclear power, but it's worth mentioning that this is a little bit more complicated, even though it gives off tremendous amounts of energy. Now, we do not get power from the power plant itself. That's a common mistake. It's almost kind of Rube Goldberg-esque. So that cooling liquid, whether it's water or something like liquid sodium, it heats up, right, to keep this nuclear power cool. And actually, we use that heating to our advantage because we run this through some thick metal pipes so radiation can't escape. And those metal pipes do transmit heat. That turns the water into steam. The steam actually turns a turbine, and that's where we get our power. At that point, we need to cool the steam down, so we run this over water. So we need to have a fresh source of water available to keep this thing running. So usually these nuclear power plants are almost always built on a river or a lake or on the ocean. And so you can keep pumping water through, cooling the steam down, and keep this running. Again, radiation leakage is a very, very small issue here. You can look back at the previous slide. There's one of those charts that shows how much radiation is allowed to leave these nuclear power plants, and it's almost nothing. A couple of quick notes. Since 9/11, the amount of radiation leaving these power plants has become restricted information, and I think that's a mistake because, we as the populace should always be aware of exactly how much environmental damage, our public utilities use or create. And, blocking that information could lead to neglect. It could lead to problems. That being said, even if this doubled or quadrupled or quintupled or 10 or 20 times the amount of radiation they're supposed to be allowed to give off, still probably not a major health issue. The one thing they do give off, though, is a lot of heat, right? All that steam cooling means that river oceans gets hot. And so, in fact, if you live near a power plant on that lake, there's probably a hot spot, a place in the river that's hot all year long, and that's because of all this heat waste coming off of the nuclear power plant. The other thing I like to bring up really quickly, there's a video on Fukushima on Frontline that's pretty good, but there's only a few minutes of it that actually talks about the science. But essentially what happened at Fukushima is that they had a backup plan, and it was in fact a really good backup plan. So not only did they have a secondary power plant to run this pump to keep the control rods cold, but they had backup lines going to 2 other power plants. In the case that their power plant went down, either of those other 2 power plants 50 miles away could still pump energy to these pumps and keep the Fukushima reactor cold. What they didn't plan on was a massive tidal wave that knocked out all 3 power plants simultaneously. So when that happened, that basically killed their ability to pump water. And what basically happened is that the cooling liquid got so hot that the control rods melted. And once the control rods melted, you no longer had control over the Fukushima reactor. And so it's now just a mess. Now they're slowly starting to take out cooling rods and power uranium rods out of the reactors that did not melt down, but that's as far as they've gotten. Basically, the only thing they're going to be able to do with this Fukushima reactor is just cage it up in a box and just leave it alone to give off radiation forever. Unfortunately, there's just no way you can save that reactor anymore.